SwayamPrabha. Digital India. Educated India.
Hello everyone. So today we are going to start with module 7, which is again dealing with the scales of turbulent motion. In module 6, we talked about the Kolmogorov's hypothesis mainly. We dealt with his 3 hypotheses and how they related to the scales of turbulence. That was the focus, isn't it? The scales of turbulence, the length scales of turbulence. And here in this module 2, we are going to do the same thing, except we are going to be extending it to Fourier modes. We are going to do a Fourier analysis of the scales. So if you remember, in module 6, what we had was we had these large scales, anisotropic large scales greater than a particular value, say LEI as we called it. Then everything smaller than that, Kolmogorov hypothesized that those small scales, those are universal. And they are universal and they are isotropic. Then there was his second similarity hypothesis brought in a new demarcation between like inertial subrange and a dissipation range. So the entire universal equilibrium range was divided into 2, the inertial subrange and a dissipation subrange, isn't it? Which was separated by LDI. So we have these 3 different scales, right? 3 different, I should say, range of scales. The anisotropic large scales, the inertial subrange, and the dissipation subrange. Now, because of these wide range of length scales, it is sometimes better to look at it in terms of Fourier modes, in terms of wave numbers, in terms of frequencies, rather than just in terms of length. And that's what we're going to try and do now. So in this module, we are going to lay out the platform for looking at length scales in terms of Fourier modes. So we are going to do look at some basics, start with some basics of Fourier transforms, Fourier analysis, and then try and take it to the Navier-Stokes equations and so on. So these are the contents we are going to be covering. We're going to look at Fourier modes. We're going to look at how Fourier series are in general represented, the evolution of Fourier modes, what I mean by the projection tensor. Then we're going to look at the Navier-Stokes equations and how the Fourier modes of the Navier-Stokes equations evolve, and then the kinetic energy of the Fourier modes. Finally, the kinetic energy of Fourier modes. So the source for this module is still Pope's book. So let's get started. So we showed you earlier in module 6, towards the end of module 6, how the longitudinal autocorrelation function was represented, and we called it f of RT in there as well. Now the Karman-Haworth equation, which is sort of out of the scope of this class, but it's something that is derived from the Navier-Stokes equation. So just know this, it is something that is derived from the Navier-Stokes equations for the longitudinal autocorrelation function. Now, as much as this equation describes the evolution of the 2-point correlation, it does not provide a clear picture about the energy cascade. Essentially what we are trying to say is the 2-point autocorrelation function does not give enough information about the energy cascade. So in order to examine the energy cascade, it is easier to look at the Navier-Stokes equations in wave number space or frequency space. So a spectral analysis is required. So, a spectral analysis would be to look at how much energy, for example, is there at each frequency. And in turbulence, typically what we do is typically what we do is we look at wave numbers. We look at wave numbers instead of frequencies. So since we are looking at wave numbers instead of frequencies, we can write the Fourier transform as follows. So here I am writing u of xt, which is a physical spaced variable. Okay, so u is a physical spaced variable and it is written as the summation over all wave number magnitudes of I kappa dot x u hat kappa comma t. So I want to make this clear. So here what I have is u, which is a vector of x comma t, is equal to summation kappa. And what do I have? I have e to the I kappa dot x. So e to the I, kappa is again another vector, kappa dot x, x is also another vector. And then I have u hat, which is also a vector of kappa comma t, isn't it? That's what I have. Now keep in mind, kappa being a vector, it has three components, kappa 1, kappa 2, and kappa 3. X, the position vector, three components again, x1, x2, and x3. Of course, x is a vector, x1, x2, x3 are scalar components. U is again a vector and I have u1, u2, and u3. U hat is the Fourier transform, is again a vector, u hat 1, u hat 2, and u hat 3. So this is what I have, isn't it? U of xt is the Fourier transform, is the Fourier inverse transform of u hat, or the summation of over all wave numbers e to the I kappa dot x and u hat kappa dot t. This right here is what I'm calling a Fourier inverse. Fourier inverse transform. Okay. Now if I take kappa dot x, what I'm obviously going to get is k1 x1 plus k2 x2 plus k3 x3. That's what I'm going to get because it's a dot product. And since I have e to the I k1 x1 plus k2 x2 plus k3 x3, this can be written as e to the I kx1 plus I k2 x2 plus I k3 x3, which is the same as e to the I kx1 times e to the I k2 x2 times e to the I k3 x3. Isn't it? So those become your Fourier modes. So essentially u hat of x comma t is summation over all wave number magnitudes. I'll explain that what that is. And I have e to the I k1 x1, e to the I k2 x2, e to the I k3 x3, and then u hat vector kappa comma t, kappa vector t. Remember, kappa itself is the wave number magnitude, which is k1 squared plus k2 squared plus k3 squared. Square root of that, sorry. Yeah, or k squared is k1 squared plus k2 squared plus k3 squared. So that's how much information that is contained in there. And I wanted to be very clear here. This is how we are representing the velocity. This is how we are representing the velocity vector as a 3D Fourier series. Using this definition, we will convert the entire Navier-Stokes equations, which is originally in physical space. We will convert that into Fourier space. Now, also keep in mind what e to the ikx is. So in general, e to the ikx is cosine kx plus I sine kx. So that's what a Fourier series is, isn't it? It is a combination of cosine and sine series. So e to the I kx by definition is cosine kx plus I sine kx. So keep that in mind. But what we are trying to do is, with this definition of the Fourier of the velocity vector represented as a Fourier series, we will convert the Navier-Stokes equations into a Fourier mode. That is what we are going to do. Okay. Now, using this definition, we can get the balance equation for the kinetic energy, and we can derive it as E hat kappa comma T is the average of U star kappa comma T times U hat kappa comma T. So remember, this is U star hat is the conjugate. U hat is the Fourier mode, and U star hat is the complex conjugate. Anything with a hat on top is the Fourier mode, and star represents that it is a complex conjugate. So here we have not derived it, but I'm just stating it here. If you want to derive the kinetic energy, you can just take a product of the velocity vector in Fourier space multiplied by its complex conjugate. So think about this. If I have a complex number a plus ib, its complex conjugate is a minus ib. If I multiply those two together, what I'm going to get is a squared plus b squared, which is essentially the magnitude of that velocity vector. So that's what the kinetic energy is representing. It is representing the magnitude of the velocity vector in Fourier space. Now, if you have multiple components, you will have to take those multiple components together. So essentially the kinetic energy in physical space is what? It is u1 squared plus u2 squared plus u3 squared, isn't it? Of course, there is a half in there. This is kinetic energy per unit mass. But if you leave that half aside, half is just a constant, then your kinetic energy in Fourier space is given by this. It is represented by, again, this is not the exact equation, we will come to that later. It is represented by u star hat times u hat. Again, complex number multiplied by its conjugate. So what we are trying to show with this equation is that if you represented the velocity vector by a Fourier series and you converted the Navier-Stokes equations into Fourier space, and then solve for the velocity, then you can get the energy by using this equation. You can get the kinetic energy in Fourier space by using this equation. And that was the goal of this entire exercise, isn't it? We are converting it into Fourier space so that we can get the energy associated with each wave number, which we could not get in physical space, because we have a velocity vector that at every point in the domain. That doesn't mean you know how much energy is associated with the large scales or how much energy is associated with the small scales. So for that, you would need to do a spectral analysis. You would need to know how much energy is associated with each length scale or each frequency. That's the reason why we did this. And this equation here is proof of that. It is showing you how we could calculate the energy associated with each wave number. Now, on the right hand side, I have velocity written with the Fourier mode of the velocity, which I would have obtained by solving for the Navier-Stokes equations, isn't it? So the right hand side is obtained. Once I get the right hand side, I can get the energy at each wave number. That is what we are trying to say. DNS, or direct numerical simulation of homogeneous turbulence, is usually performed in this wave number space. This is an application of that. We do direct numerical simulation in wave number space, and one of the primary reasons for doing direct numerical simulation in wave number space is because there are no truncation errors. Remember, when you take the Navier-Stokes equations and convert it into Fourier space, you are getting rid of all derivatives. I'll show you an example of that. For now, just take it from me. When you convert it into Fourier space, we are getting rid of all the derivatives. If you get rid of all the derivatives, you're getting rid of any discretization associated with it. And if you're getting rid of all discretizations associated with it, you're getting rid of all truncation errors. So that means, believe it or not, there are no truncation errors when you convert your Navier-Stokes equations into Fourier space. They are exact. They are exact. You are getting a perfect solution. Obviously, there are some requirements to it, and we will come to that. But that is the context. That is the platform, that is the motivation for why we are converting it into Fourier space. I hope this is clear. So now let's take a step back and look at the Fourier series representation. What does that mean? Now, one of the requirements of a Fourier series is that you need to have a velocity field that is periodic. Okay. Now this is a very strict requirement. You will realize that it is not always the case that a turbulent velocity field is periodic. I mean, it is hardly the case, in fact. So, but it is a requirement of a Fourier series representation. So think about it. If you have, let's say, some kind of domain, and in this particular case, let's consider a cube that has a side L. So each side has L. Volume is L cube, isn't it? So in physical space, I have the length, width, and height of the cube going from 0 to L. Now, let's say this length of side L is large compared with the turbulent length scale, meaning it is large compared with the integral length scale. So what we are trying to say is each large scale is contained within this cube, isn't it? Now, if you are using a Fourier series representation, then your velocity field is supposed to be periodic. If it is periodic, this is what it would look like. It would be u of x plus nl comma t is equal to u of xt. N here is the number of is for all integer vectors. That means how many ever times you cross L, which is the length of the cube, you are going to repeat your velocity. So if I just draw it in terms of a 1D representation, this value here and this value here, say 0, 1, is the same. Then I repeat it again, and then I have 1 and 2 being the same. Okay, so this is 1L, this is 2L, if you will. So u of x plus nl, n being any integer, nl comma t is the same as u of xt. So it keeps repeating itself. That's what I mean by periodic. It keeps repeating itself. Now in the x1 direction, let's say we are only writing it for the x1 direction, the Fourier modes are of complex form. So I have e to the I. Now look at what I've done here. Earlier I had k1x1, isn't it? I was writing it as k1x1. See here, I was writing it as k1x1, e to the I k1x1, right? k1x1. So instead of writing it as k1x1, I am going to write it as k0n1, where n1 is a set of positive and negative integers and k0 is the lowest wave number. K0 is the lowest wave number associated with the largest length scale, and the largest length scale is the size of the cube. So I have 2 pi over L, which is going to be the smallest wave number, and all other wave numbers are multiples of the smallest wave number. Makes sense. So if your smallest wave number is say 1, then you will have 1, 2, 3, 4, so on and so forth. So it is all integer multiples of the smallest wave number. All your wave numbers are integer multiples of your smallest wave number. So k0 n1 meaning k0 times n1. So that, like we represent e to the ikx, it is cosine plus I sine, isn't it? And remember, n1 can be positive and or negative, and k0 is the lowest wave number. It's going to be a positive number. So I hope that is clear. So that's your Fourier series representation, isn't it? Now if you define a wave number vector k as k0n, where n being a vector again and k0 is this lowest wave number magnitude, then you will have, you can write n as in n vector as e1n1 plus e2n2 plus e3n3. The whole thing multiplied by k0 gives you your k, or kappa I should say, which is the wave number. So kappa vector is kappa naught n, which is kappa naught times e1 n1 plus e2 n2 plus e3 n3. What are e1, e2, e3? The direction cosines. Simple enough. They are the direction cosines. In which case e to the I kappa dot x is e to the I kappa naught n1 x1, e to the I kappa naught n2 x2, e to the I kappa naught n3 x3. This is exactly what I wrote earlier, isn't it? This is exactly what I wrote earlier. Instead of writing it as kappa naught n1, I wrote it as k1 n1, isn't it? This is k1 n1, k2 n2, k3 n3. Follow me? So here I have e to the kappa naught x, e to the I kappa naught n1 x1, e to the I kappa naught n2 x2, e to the I kappa naught n3 x3. So these are your three Fourier modes in three directions. And you also have a Fourier, a wave number magnitude, like I was saying earlier, which is kappa, which is just represented as kappa, which is the modulus of kappa wave vector. So kappa is modulus of kappa vector, which is square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. And your direction cosine, like I was explaining earlier, is this one here, which is kappa vector divided by kappa magnitude. Kappa vector divided by kappa magnitude, these are the definitions of the direction cosine and the magnitude as well. Now, one more thing we want to bring in, a couple more things we want to bring in. If you have two wave number vectors, kappa and kappa prime, two wave number vectors kappa and kappa prime, then the Kronecker delta, delta kappa kappa prime, is equal to 1 if kappa is equal to kappa prime and is equal to 0 if kappa is not equal to kappa prime. This comes from the Kronecker delta definition, where delta ij is equal to 1 if I is equal to j, and it is equal to 0 if I is not equal to j, isn't it? That is exactly what I've written here. It is equal to 1 if kappa is equal to kappa prime and is equal to 0 if kappa is not equal to kappa prime. So that's that. And then the other denomination we are bringing in here is, let's say we denote, okay, this average symbol with a subscript L, meaning it's a volume average. Volume meaning the volume of the cube, averaged over the entire cubical volume. So this angle bracket subscript L, let's say it is the volume average over the cube 0 to L. So xi going from 0 to L. Then the orthonormality property can be defined like this. We won't get into the proof of this, but this is the orthonormality property. So I have e to the I kappa dot x, e to the I minus kappa prime dot x kappa prime dot x averaged over the entire volume is going to be equal to the Kronecker delta, meaning it is going to be equal to 1 if kappa is equal to kappa prime, and is going to be equal to 0 if kappa is not equal to kappa prime. So I hope that is clear. So this is the orthonormality property that is satisfied for Fourier series. You should check that out. So we are not going to get into the proof here. The orthonormality property, I'm stating it as such. So I have e to the I kappa dot x times e to the minus kappa prime dot x, the whole thing volume averaged, is equal to the Kronecker delta. And the Kronecker delta is 1 if kappa is equal to kappa prime and it's equal to 0 if kappa is not equal to kappa prime. Okay? Now, so with that as the definition, let's define a Fourier series for any periodic function g of x. So for any periodic function g of x, its Fourier series is given by this. G of x is just like I had defined earlier, isn't it? A summation over all kappa vectors, e to the kappa dot x, g hat of kappa. And the sum is over the infinite See, there is no limit for the kappa vectors, right? Sum is over the infinite number of discrete wave numbers, k0n, where n is again a vector, and g hat of kappa is the complex Fourier coefficient at a wave number kappa. Since gx is real, g hat of k satisfies the conjugate symmetry, so g hat of kappa is g star of minus kappa. The conjugate symmetry is always satisfied by the Fourier series. So because g of x is a real, it's a real variable, right? So g hat of kappa is the same as the conjugate, is the complex conjugate of the negative wave number. So the asterisk is representing the complex conjugate. Now that you have the Fourier series and this conjugate symmetry property satisfied, you will have g of x times e to the minus I kappa prime dot x volume averaged, okay, would be equal to, I can substitute, instead of g of x, I substitute this. This is substituted for this part. So I have g hat of kappa e to the I kappa dot x times e to the minus I kappa prime dot x. Then what happens? I can take the g hat of kappa out of this volume integral. Why? Because the volume integral is physical based. G hat of kappa is Fourier based. So the g hat of kappa would be a constant with respect to the physical space. So I can take it out of the volume average. So then what I get is g hat of kappa, isn't it, multiplied by the volume average of e to the I kappa dot x times e to the I minus kappa prime dot x. Isn't it? Volume average. So this becomes, there you go, the Kronecker delta. So I have g hat of kappa times the Kronecker delta. By definition of the Kronecker delta, if I have g hat of kappa times delta kappa k kappa prime, and because the Kronecker delta is equal to 0 when kappa is not equal to kappa prime, and it is equal to 1 when kappa is equal to kappa prime, the g hat becomes a function of just kappa prime because everything else goes to 0. So that is what we have shown here is the volume average of a physical space variable like g of x multiplied with its Fourier coefficients, or the Fourier coefficients e to the minus I kappa prime dot x gives you the Fourier mode of g of x. That's what we are showing. So we have laid the groundwork here for converting the Navier-Stokes equations into Fourier space by defining the Fourier representation, by looking at what the definition of the Kronecker delta is, what the orthonormality property is, how the wave number vector is defined and all that. And we have come to the point where we are now defining this volume average of a physical space variable multiplied by the Fourier mode gives you the Fourier mode of the physical space variable, g hat of kappa prime. Okay, so in the next class we will now take it by applying this to the Navier-Stokes equations and look at the Navier-Stokes equations in Fourier space. Thank you.